Hello, students. I'm sorry I couldn't get my webcam to work earlier, but this is me down in the lower right-hand corner. I forgot to start the recording for the class session until about midway through. So I'm going to re-record what I went over in the first part for those of you that couldn't access the first part of the video. So what I have shown right here is the Canvas web page, and I'm just first going to kind of go through this. I know many of you have been using Canvas and you're quite familiar with it, but each professor kind of organizes their course a little bit differently. I'm using a modules format. So each of these blocks here is what's called a module, but I really think of the class as having the modules that are listed with these themes, nature of science, what is matter, those kinds of things. And there are going to be some blocks in between that are simply just for tests and quizzes. I don't consider those to be separate modules. So what I want you to do, if you haven't done so already, is to go through the first part here on the welcome. The instructions page will tell you each page you will need to address and help you to navigate around into Canvas. I want you to introduce yourself. Most of you already have, but there are a few of you that still need to. There's a practice quiz, and that will just show you how to do the different types of questions. Maybe you've already done all of them. Maybe you've only done multiple choice. Sometimes I'll ask for a numerical answer. Sometimes you'll have matching or drop down. And I want you to see how those work prior to seeing them on a quiz or a test. And then I also have here for submission, and this is just for you to use the Rocketbook app to submit materials. So I've asked you to download Rocketbook. The app is free, and you can print off the pages there's no charge to get those pages. If you do not have access to a printer, please let me know as soon as possible, and I'll mail you some copies of those pages that you can work with through the next few weeks. And then finally, there's some old exams and quizzes. These are primarily from when I teach the class in live and in person, and so they're paper tests and quizzes, but they're good examples of how I ask questions on different topics. Okay, so the next section, well, before I go on to that, I did want to point out a few things that can be helpful to know where things are on here. One is the syllabus. So since we're not in person on the first day, I can't hand you a syllabus, but you can click here and you can see what would normally be on that paper assignment. So this is my office number. Now I'm not always in my office, and over the summer that might not be the best number to reach me at. So I will send you an email with that number. And then we have, some of the typical things that you'll see here. But what you might be interested in is the breakdown of how the grading works. Because this isn't a majors level class, I don't have quite as much weight on the tests as I normally would, and more of the weight is on assignments and responses to some of the things that we do in class. So those are an important part of the grade, and it's not just a matter of, go in and do the tests and do really well on those. And so you can see some of the other typical things in here. And all of you, I believe, have logged into Canvas if you are watching this. So you know that you need to log in by the 5th day of class, or the registrar will remove you from the class. So if you know somebody else in the class who isn't really responding, you might want to give them a little bit of a nudge. All right, so the next thing I want to look at is the modules. So nature of science is one of our modules, and what is matter. So those are modules 1 and 2, and those are going to be what we'll cover in the next week and a half of class. And unlike the other modules, this nature of science module, I'm going to have you do it at the same time as the other modules. And this is because you're going to be doing more reading and writing in response to things, and you're going to need some time to find the articles and so on and so forth. So in between, you can be looking at the things from the other modules. And I'll go into more detail about what's in this particular module in a few minutes. When you have your different modules, they're going to be set up in a way that you can kind of read through and click on each thing. But each module will have a page, this little green thing that kind of looks like a paper, that deals with the chapters in that module. So I'm going to click on this chapter 17. And chapter 17 is the appendix for your book. And so this is the only place they address the scientific method and the nature of science and those kinds of things. So each of these pages for each chapter will have a list of the goals, the things that I want you to be able to do. And so you can read through that and see, oh, do I know how to do each of those things? And then it will have a section that says do this. And so these are the tasks that you need to do. Now, some of them are things that, I'm obviously not going to grade you on reading the chapter, because I'm never going to know whether or not you read the chapter other than how you respond to things. So, you just need to, you are going to be held responsible for that, but, that's obviously not like a grade in the grade book. There are going to be links to some things. So, for example, this is a link to another page. Rather than putting all of this content on this page, I have a separate page here so we can go to scientific studies and read in more detail about the scientific studies. And I'm going to refer to these 2 pages on coconut oil. They're very different in how they present information on the benefits of coconut oil. So we'll talk about those in a little bit. And then you can always just use your browser to back up to where you were before. There are also going to be some videos. So sometimes they will be going over or reviewing skills that you might need in the chemistry. In this case, these are about generally looking at information that you receive on the web and how you can determine whether or not you can trust it or how much you can trust it. It's just general information, not scientific information, but some of the principles are going to apply across the board. So this first one is on facts and fact checking, and the second one is on who you can trust. And so hopefully that will help you to be able to take in information from the internet and really think about it critically and decide, is this information that I want to hold on to or forward on to friends, or is this something that's probably not worth that? So we have those. And then you'll also have some links to some tasks that you need to do. So for example, this says respond to this discussion, and there's a link here. Now I've put all of the graded work down at the bottom as well. So it should be in the do this, so you can click on it, but it's also down at the bottom. So if you want to make sure that you have completed all of the assignments, you can go down here and click on these, make sure that you've done each of these things. Generally, each module will have 1 or 2 quizzes. And so that will probably be the last thing within the module. And then after 1 or 2 modules, you'll have an exam that covers the content up to that point. Now, it might seem like it's hard to keep track of all the things you need to do, especially if you are trying to do 2 modules at once. So if you look on the right-hand side, you have a to-do list, and it will put in order the things that you need to do with their due dates. But there's also a little link here that says View Calendar. And if you click on View Calendar, it will kind of give you a timeline of things that are coming up. So if we look at this coming week, you can see that I've put kind of the introductory materials due today. And then we have some of the stuff about the first discussion and some of the stuff from the first chapter. So isotope symbols is due at the end of the week. So I'm going to try and gather the due dates in about 2 spots during the week. That doesn't mean wait until that point and do that. You can spread them out, get them all done at the front, however you want to do it. But we want to make sure, I want to kind of keep the due dates as consistent so that you kind of know what to expect when those are coming. Now, if we look at the next week, take a second to load here, we'll see some here. I haven't posted all the assignments yet, so you'll see some more that are appearing here after your first exam. So your first exam is June the 3rd. But I have front-loaded a lot of the assignments. And part of this is because I want to address that nature of science early on, and it covers everything, but also because I know a lot of you are familiar with the structure of the atom and the periodic table, and so you can go through that material pretty quickly. So if you're not one of those people who feels comfortable with that, please make sure you're in contact with me or that you're making use of the practice items. Let me get back to the main page here for a second. You'll notice that at the end of the modules, you'll see practice and help. And these items are items that are simply there for you to practice something. Obviously, if you need to see if, do I understand this as well as I think I know? And then sometimes it's a link to a video or a web page that explains it a little differently than I would or the book would. And so maybe that'll make things click a little bit better for you. So those are never graded. They're not part of your grade, but it's there for you to use if you're struggling at all with the class. Okay, so the next thing that I'm going to do is I'm going to go to PowerPoint. So let me pull that up here. If this will move. There's PowerPoint. So I had some topics that I wanted to make sure that I covered today. So I want to hit these things. So one of the ones that's not on here, somebody mentioned it earlier this morning. I'm switching from a book I used to a new book this summer. And so the old book is Hill and Kolb, Chemistry for Changing Times. If you see references to that, that is not the book that we're using. We're using the general organic and biological chemistry that is listed elsewhere. So you only have one book that you're looking at. It is fine with me if you use the online. It is fine with me if you use the hard copy. I will be making reference to pages in the hard copy. I'm not exactly sure how the online is organized. Okay, so some important points, and I'm going to pop this up here. You are taking this probably because you're trying to fulfill the requirement to take a course in the sciences. And the reason why we don't have you take a biology, a chemistry, and a physics and a geology and say each one of these things is important is that there are some cross-cutting themes that regardless of the science that you take, you're going to see these things. And these are kind of the important part of understanding what science is and how it works. So one of the most important things is recognizing patterns. And science is about seeing those patterns and using those patterns to make predictions, particularly about the causes and effects related to natural phenomena. So, so we'll see that quite a bit, particularly in this nature of science section, trying to suss out what are the causes and effects of things. We'll have scale, proportion, and quantity. This is kind of the math portion. Many of the phenomena that occur naturally are happening either at a scale way too small to see. For example, a lot of chemical reactions, or all chemical reactions, are way too small to see, or way too large to see, like astronomical events. And so we use scale to put those in proportion to where we can work with those. And so there's going to be a little bit of math involved. We also use the idea of systems, of groupings, or of particular things that work together. For example, all the parts of the atom working together to make the atom act the way that it does. And then we use models of those systems. And so those models are really just ways to help us understand a very complex system. And we usually simplify them. The models may be something that is a physical thing, a drawing or a three-dimensional model, or they may be ideas or analogies. So we might say an atom is like a solar system. So I don't have a physical thing that I'm sharing with you, but you know what a solar system is, and we can use the analogies between those in order to understand the atom. We also have energy that is a major part of science, regardless of where it's, what kind of science we're looking at, and the matter that is involved with that. And that energy is transferred from object to object, or it is transformed from one kind of energy to another. But the energy is never lost. So this is kind of one of our first principles that applies. We call it the first law of thermodynamics, but applies to all sciences. In the entire universe, the energy doesn't change. We never make more energy. We never lose energy. It's never destroyed. So when we think about energy and we use energy to do things, we use energy for ourselves and for what we do during the day, but we also use it for electronics, for lights, for cars, and things like that. Using that energy means we have to think about where is that energy coming from? How can we use it efficiently? And then sometimes we really need to think about where does that energy go once we're done using it. All right, so the last couple of things, stability and change. So stability, we're going to see several laws that are conservation of. I just mentioned conservation of energy. We'll also see conservation of molecules or matter. I'm sorry, I shouldn't say conservation of molecule, conservation of matter or conservation of mass. So those are things that stay the same, but of course, for anything to happen, we have to have some kinds of change. And those stability rules kind of govern how change happens. And we'll see a lot of things will happen in cycles. And then finally, the idea of structure and function. So we can think about the way that our teeth are shaped helps us to chew our food in a particular way. And that's why we have the incisors are a different shape than the molars and so forth, because we might have cutting versus grinding. Well, we have the same thing with molecules. Depending on functional groups that we put on molecules, the shapes of the molecules, we might get a different scent, or we might get a different ability to bind with a protein, or we might get a different ability to clean. And so the structure of our molecules will affect the function of them. All right, so I'm not going to test you over memorizing these themes, but you will see them appearing again and again throughout the course. And as you are going through things, when you see something that refers to energy or refers to stability or refers to cause and effect, those are probably ideas that I really want you to focus on. All right, so I walked through on Canvas how the format is. For each module, you're going to have some readings. You'll have some assignments. Those are listed under the graded work. I'll try to list those also on the modules page so that you can quickly get to them rather than having to go into the page itself. And then there will be usually a quiz. Sometimes there'll be 2 quizzes. Now, with your exams, you'll have to do them on a particular day, but all of the assignments other than that, they'll be open up until the day of the test. So I'll offer a due date just to kind of keep you on track on where I think you need to be, but you are welcome to do those early, and you can do those a little bit later. Now, if you wait until after the test to do those items, if they are still open, you will probably receive a grade penalty on those things. Because I want to get those things graded as much as possible. The one thing that I really want you to do on time is the discussions, because if you wait to do your part of the discussion and somebody needs to respond to you, then that makes it harder for them to do their assignment. If you need the practice, I expect you to do those practice items without my having to say, do this practice item. If you know that you're weak in an area, you should be going and doing that. Now, the way the test will work, you will have a test date. So your first test date is June the 3rd. The day before that, at 10 a.m., I will open the test. So you can start from 10 a.m. of the day before all the way until 10 p.m. of the day of the test. Now, for those, the test is open for 36 hours, so you will have the opportunity to start the test during that time frame. So hopefully, regardless of jobs or whatever else is going on, you'll have an hour in there that you can do it, but you only have an hour once the test is started. So make sure that you're not planning on starting and stopping, starting and stopping. I've given you an hour for each test, but I find most people are done in about a half an hour, maybe a little bit more. So that should be plenty of time. But if you are somebody that needs special accommodations that you normally get the extra time and a half on a test or something like that, make sure you contact me, and that you also contact the Student Success Office so that they can send me the letter of accommodation, so that I know that I'm allowed to give you that additional time. You probably won't need it, but I know sometimes just knowing that you have it can reduce your anxiety level. So we'll make sure that that's available for you. All right, so I had wanted to address a few things with the nature of science. Your book doesn't go into a great deal of detail on some of these things. It does talk about the scientific method in those few pages in the appendix of chapter 17, but it doesn't go into as much detail as I normally like to. So we commonly use the idea of a theory in everyday life. We kind of toss that word around, and sometimes it means what scientific theories do, and sometimes really when we say theory, what we really mean is a hypothesis. So a hypothesis is really focusing on just limited observations, maybe just for a particular circumstance, whereas a theory is really trying to tie together many, many observations, usually made over many, many experiments, and often by many scientists. And so there's a lot of work and study and experimentation that has already gone into the theory. With a hypothesis, maybe we've never even done a test. Maybe we've just made an observation that, hey, it's cold outside and I don't see any birds. And so that's what I'm going to make my hypothesis about. I think the connection between these two things is this. So very limited on a hypothesis, with a theory much broader. We sometimes use the terms theory and model interchangeably, and they really are very different. With a model, we're trying to simplify something that's very complex in order to explain it, to understand it, to teach it. So we know with a model that we're not taking into account every little piece of that object or that idea that we're trying to explain. But we're trying to make it simple enough that whoever is looking at the model can get the important information they need out of it. So when we're looking at a model of an atom, we might draw a picture with rings or with circles for neutrons and protons, and we might have the scale completely off, and we know that maybe that the letter E or a plus symbol doesn't actually appear on these things. Those aren't going to interfere with our understanding of the locations of those different items, which is what we're really trying to use that model for. A theory, on the other hand, is really trying to incorporate all of our observations and make sure that the explanation works in each of these scenarios. So if I find something, an observation that doesn't fit into that theory, then I'm going to need to modify my theory in some way that explains this observation. Or I might need to find out, well, maybe this observation isn't a legitimate observation. So we have to pay attention to those things. So we're pretty sure our theory is right. And generally, theories are things that have been worked on by many people. Many different scientists have put their work into it, and they get tinkered and fine-tuned with. We don't throw them out completely if we need to change them, but we modify them in order to make them look the way that they should. Now, a theory is one of the most certain things in science, but we're never 100% in science. So a law is the closest we get to being 100% certain. And that is just an observation. So if we take, for example, the law of gravity, it simply states that when there are two massive objects, they are attracted to each other. It doesn't say why this happens or how it happens. There's no explanation into it. It's just the observation that whenever there are two things with mass, they are attracted to one another. And in order for it to be called a law, there can't be any exceptions. It's something that's universally agreed upon by scientists. You're not going to find a rogue scientist somewhere that says, no, I don't believe in the theory of gravity, because it's not a theory, it's a law. So once we find an exception to that, then we'd have to alter that law or get rid of that law. But with a theory, we're explaining observations, and there can be lots of different ways that we might explain things. So we might all look at the same event and explain what's going on in that event in different ways. Now, because scientific theories have been worked on by many people and fine-tuned over a long period of time, most scientists are going to agree with them. And so the ones that you read about generally are the ones that 99.99% of scientists agree with. That doesn't mean that there aren't legitimate scientists who might have questions about part of the theory or who have alternate theories that can explain those things. So it's slightly less certain than a law. Laws we don't really see anybody objecting to, but theories you might find some people with legitimate um, objections that they think there's a better explanation somewhere out there. All right, scientific certainty. Um, Scientific certainty refers both to um, the precision with which we understand something, so how repeatable this experiment is, or how precise we can be with our numbers. Is it about 10%? Is it 10.5%? Is it 10.55583%? So that is kind of a discussion of certainty, but it's also about whether or not we believe these things to be true. And the first thing I have on there twice because it's really important to understand. Scientists don't prove things. Science experiments never prove. So scientists will gather observations. They might show a connection between things, and they may have a lot of evidence. But with science, we can't look at every possible example that exists. And in order to prove something, we'd have to account for every possible instance. And we can't go to the entire universe or the entire history of time and look at all those examples. Now, you may have had proofs in math, and in math, you can prove things because you can say, this is true for this number and this number plus one. And if I can show that for that number plus one every single time, eventually I'm going to hit all of the numbers. So you can account for all of the numbers in a mathematical proof. In science, we can't account for every possible situation. All right, so scientists are going to use repetition and statistics to show their certainty. So the repetition might be having a lot of subjects in an experiment. So you might have 100 people in your trial, or you might have many, many trials. So you might do the same experiment over and over again. And how much you need to repeat really depends on what it is you're studying. So chemicals and objects tend to behave the same way every time. And so we maybe don't need as many repetitions. But if we're looking at living things, because there might be mutations, because there might be subtle differences in environment, we might need more. And if we're looking at people, people have free will and they're influenced by their background, by their culture, by the environment in which they were raised, and all of those things then can affect how they respond to whatever situation we're trying to study. So we'd need a lot of people, thousands of people, to really be sure that we were on track with that. Now, when scientists do a study, they're going to submit it to a journal. This is how we share information in the scientific community. And so what's important to understand is that, first of all, scientists don't get their ideas accepted by simply going out and saying to people, hey, this is the way it is. They generally are going to publish that, or they might take it to a conference and discuss it at a conference. Now, in order to publish in a journal, then you need to submit it, and it will be reviewed by maybe 4 or 5 different people. And those 4 or 5 different people are going to be experts in your field. So they're also going to be knowledgeable about what you should have done and how you could have controlled your experiment. They're going to look at, did you set up the experiment correctly? And they're going to look at, did you draw good conclusions when you were doing your experiment? So does your conclusion follow from the experiment that you actually did? And then the final thing that they might look at is, Are you saying something new? Are you saying something important? And so after the reviewers look at all of these things, then the editor of the journal will decide based on those reviews whether or not it gets published. And if there are flaws in the science, then they're not going to publish it. And then depending on the journal, they might say, well, maybe, it's a good study, but you're not saying anything new or interesting or earth shaking, depending on the level of the journal. So the journal Nature really only publishes, wow, this is a really big deal, new idea. So my tiny little study of these two chemicals over here isn't really going to get into that. But something that really fundamentally develops a theory or alters a theory is going to be more likely their speed. So you can see here that some journals, you're going to get less than 15% of the submitted papers will be accepted. So that tells you that this isn't just oh, I'm done, I'm turning in my assignment, it's going to get published kind of thing. It really has to be scientifically sound before it ever gets to that journal. Then once it's in the journal, all of the readership are people that are knowledgeable in science. And so they're going to be people that are going to be thinking critically about it. Did you consider this? Did you look at these examples? All of those things. Why did you only have this number in your study? Did you look at a broader set? Did you look at a more diverse set? And so all of those things are ways that scientists check each other to make sure that the ideas that we put out there are ideas that are sound. So when you see something that has been published in a journal, you know that there is a lot of what we call vetting of that idea, that there's a lot of testing and reading and looking through and making sure that this is a sound idea. This isn't just something somebody came up with one Saturday morning and popped it off and said, hey, I think this is what's going on. It's really been something that has been looked into quite a bit. So while when we say we're not proving anything, that might make you think, oh, well, then how can we trust science? They never prove anything. Really, there's a lot of work going into being fairly certain about what's going on. So it's not 100% proof. It's possible there's a scenario we haven't considered or a situation that's different, but we have a whole lot of evidence that says that this is true.